I've been at D-Wave for about 16 years now. My background is in physics, and I lead the teams that build the quantum computer at D-Wave, the physical technology. And I want to get into this. I'm going to with covering three major areas. One, I want to give you an overview of D-Wave as a company in terms of the distribution of what are different people doing and how does that break down. I want to talk a little bit about how that applies to what we're trying to accomplish. I want to get into a little bit around the challenges of then hiring and recruiting the workforce for that. And it is a challenge. And that's to sort of lay the foundation for the main point for this section, which is around the bottom line is we end up needing to do an awful lot of training on the job. And we've developed sort of systems and methods for that over the years, and approach to that over the years. And so I was actually really intrigued to hear what some of the creative things that you folks were thinking about in the last session. So at a top level, in a coarse-grained way of breaking this down, D-Wave is very, very vertically integrated. And vertically integrated in a couple of ways. And I suspect that what I'm going to say here applies to a lot of the providers, a lot of the quantum providers. We're vertically integrated. So what I'm showing here is basically the breakdown of employees. There are about 190 folks working at D-Wave. About 40% of those are involved in developing the physical quantum computers, the physical systems. I will confess to you right now, that's my own myopia. And at some point I will descend into focusing mostly on that, but not entirely, because about 20% of the company is basically common areas or corporate. So for example, HR, IT, et cetera. About a quarter of the company is required for the software and cloud. So this is around not only do you need to build the quantum computer, but an important part of our go-to-market is around developing a quantum cloud service to make this computation available to folks to develop the hybrid algorithms that make it easier for customers to use that. That's about a quarter of the company. And then about just under 20% of this company is go-to-market. So that's sales, that's marketing, but that's also professional services. And that comprises very technical folks that are really good at, maybe folks that might have been trained by an Umesh Vasarani, who are really expert in quantum algorithms, that are expert in classical algorithms, and that can reason through and problem solve as to how to connect customer problems to the quantum hardware. And you need all of that to make a successful go at we believe this is the right way to develop quantum computing. Now zeroing in on the quantum computer itself, this is also a very vertically integrated technology area. So for example, we've got folks that are designing, and then also folks that are fabricating the superconducting integrated circuit chips that are at the core of the quantum processor. We've got electrical engineers that are developing the electronics, the room temperature electronics that are driving those systems. We have cryogenic, mechanical, et cetera, engineers that are helping to productize and develop the cryogenic systems that we put our systems in. We, a few years ago, made a strategic acquisition to acquire the company that develops the PC boards, with whom we had worked to develop the PC boards that make our processor mount with aluminum superconducting traces, because that was a very unique technology that we worked with them. And there are actually there's some other companies in the conference here today that actually contract with that company, because this is it's one of the sort of the unique and alien aspects of the technology around quantum computation. So all of this is part of a sort of a very large vertically integrated system, and that brings with it some challenges. One is, let me get to that in a second. There's some management that makes management complexity, because all of these different parts have to work together in a timely fashion. It also means there's a lot of this where we find that we're not hiring for folks directly out of the university that are trained to work in many of these areas. There's a lot of on-the-job training that's required. One of my favorite examples is superconducting circuit design. It's not something where there's an accredited engineering program anywhere that I'm aware of in North America where one can learn this. the last academically trained fellow we hired for this we got from a program out of Stellenbosch University in South Africa, so literally going to the ends of the earth to hire somebody with this expertise. But we've since come to terms with that and actually now have an approach towards basically hiring from adjacent areas, more common areas in electrical engineering, finding people that are willing to learn and adapt and develop into the new area, and we train them here. So then around how building the team, there are a couple of points I want to make up at the top here, and this is just sort of to give you my mindset when we're going around hiring. And this particular quote by Leoncini, we could have used a number of different sort of pick your favorite team building quote. This one is particularly important to me, but I just wanted to mention, I think it was Robert Joint in the last presentation mentioned the importance of soft skills. This is really a critical point, is that for us, problem solving requires it's not just individuals. People have to be able to work together. They have to be able to work well together. When we're hiring, this is front and center. It's relatively straightforward to ascertain if somebody has a good technical background and determine that when you're hiring. It's much more challenging to find if they're going to be a good team player, if they're going to work hard on something and not be obsessed with getting credit for it, or will be working together and not undermining colleagues and form be part of a constructive team. So this is just, I'm glad to see that some of the providers are thinking about this as part of the mandate, and it's an important part of the mandate. It's not uniquely quantum, but it definitely is important in this context. And then around problem solving, and this is our general approach, we find that when we are not able to hire people with the specific skill sets we need, really what we're looking for are people that know how to solve problems. And it's much easier to teach somebody who is a good problem solver a new skill than it is to try and train somebody how to solve problems. I do hope that we are all engaged in that anyway, but it's just that's a much harder thing. So we really are not fixated on did you know exactly the right programming language or exactly this type of electrical engineering, but we hire based on the idea of that they're good problem solving. So we do an awful lot of mentorship in-house, where the expectation on hiring is that, depending on the area, some is different. The expectation is that it may be 6 months or a year before they're really fully up to steam on being able to work with one of our multi-thousand qubit processors and develop it to the point of releasing it. The calibration of the processors, for example, there's a lot of working together with people, senior and junior people paired up. A lot of this was very severely challenged by the pandemic. The folks working on the systems, it was very important for us that we're sort of co-located, that we're together. People found ways of making it work remotely, but it's been very important for us to be able to get back together, to be able to stand shoulder to shoulder in front of a whiteboard or in front of a screen, to be able to reason through a problem. We're human, we're animals that communicate by various channels, not simply just verbally. You all know that because you've chosen to come to an in-person conference. One of the things, though, we gained to overcome the challenge of of COVID and being remote, we had people that were just starting, and then we're in this of like the office is empty. How do you onboard them? So there's a lot of very deliberate lectures that were recorded. A lot of material was developed during that process, and that's actually improved our onboarding approach, because now we have this reservoir of lectures that folks can watch that were very well thought out. So it wasn't all. We also, I just want to touch on co-ops and internships. We think are very important. Now we're a Canadian organization, so it's much easier for students for us to hire from Canadian universities. But this is a really important part. It's the same theme that Alan Ho had touched on, the value of getting students exposed to quantum computing and all the other parts of the puzzle, the various types of engineering, computer science, et cetera, that are required to make the whole system. So I think I'm out of time. Yeah.
What I wanted to address here was the importance of hands-on quantum education in strengthening the workforce element of the quantum supply chain, and kind of this idea of how that starts with what we're calling the quantum spark. So it's a bit of a divergence from what Mark was talking about. It kind of talks about some upstream stuff, but I think it's still relevant. So I'm just going to go for it. As an 18-year-old high school senior considering a career in engineering, I took a tour of the University of Rochester optics department, and with no idea of what a optical engineer was or did. And I end up in this lab that's filled with equipment that I don't recognize, I've never seen before. And my immediate reaction is, all right, don't touch anything, don't break anything, keep your hands to yourself, we'll survive this. But the next thing I know, there's a laser beam bouncing around the table, and I'm told that we're gonna make a hologram. So I got lasers and holograms. I'm like living out my Star Wars fantasies in this little lab here. So, I so vividly remember adjusting the mirrors and the lenses and adjusting path lengths. And all the while, this little white chess piece pawn, which was our subject, was glowing in the red laser light. It was, obviously burned into my memory. This was a long time ago. But that one afternoon convinced me to go down an education and career path that never would have happened if I did not have that spark. And so when we talk about a quantum spark, it's the idea that it's that one unique and intriguing experience that a young person can have that shows them that this is possible for them, and that they can then envision their own personal contribution to the quantum science. So that's what I would like to explore a little bit more in this, and how do we create that quantum spark in the next generation of scientists? So quantum is hard. It's hard even describing what it is in an understandable way. So this stuff is really intimidating, and that intimidation can be a true barrier to entry for young people that haven't had the exposure yet. But I think that this intimidation is also our opportunity. And that's because there's also a fascination with the unknown, with the complex, with the counterintuitive that kind of teases this potential for discovery that taps into our creativity. And so quantum is going to change the way that future generation of humans live on this planet. And I think that we should invite them to be part of this creation as a community by providing hands-on learning tools to give them the opportunity to have that spark. And I think that that could be the best way to take down the barriers of intimidation that so many people likely experience, and illuminate their path forward into quantum science. And so as a product manager, I talk with our sales team about the sales funnel. I talk with our engineering team about the project funnel. Well, this is the brain funnel. And so we need more minds engaged in this science, not just at the PhD level, but all the way through undergrad and even into the high school level. And I think that the challenge today that we have is there's not enough support for the educational bandwidth that we're going to need to provide a workforce to supply the labor market of the quantum industry. And I think we solve that by going way upstream and not doing more with the less that we have now, but creating more for us to do more with. And we do that by providing early hands-on exposure with the potential, which has the potential to expand this funnel, bring more brains into the quantum ecosystem, so that we have scientists that are pushing our knowledge forward. We have engineers to use that knowledge to create the machines and the systems and all the equipment that we're using to build the quantum infrastructure that we're going to need. So to bring this more to a practical level, imagine a candidate pool that is already familiar with the equipment, that is familiar with the experimental methods, that's familiar with the end use applications of quantum tech. It creates a workforce that does not need quite as much on-the-job training. So, employees get spun up faster, they get onboarded faster. Research and development projects can start quicker and progress more quickly. And companies can scale and ramp faster because they have the resources that they need to do that. So the idea, if our goal is if our goal is hands-on exposure to quantum science, there are a lot of pieces that need to fall into place to do this. But we have started already. The QEDC quantum roadmap identified cost and complexity as a barrier to a robust quantum ecosystem. And if we understand that as especially poignant for hands-on education, the cost and complexity that can prevent that hands-on education then affects the health of our future workforce, years down the road. And so I think, simplifying cryogenics is something that Montana Instruments has done. It's at the core of what we do. And so we decided to take on the cost aspect of this and take the first step toward reducing the price of some potential hands-on teaching lab modules. And so our engineers struggled mightily to figure out how do we pull out enough of our cost, but still maintain the quality, the reliability, and the ease of use that you're going to need for the cryogenic equipment to be an invisible piece of the quantum experimentation. And so we developed the CryoCore, which I think is the perfect teaching tool. It's easy to use. It's versatile enough that it can demonstrate a number of basic quantum phenomenon. And it can do it affordably because it's more than just this piece of the equipment that you're going to need in a lab module. So this isn't cheap stuff. So I think we succeeded in that mission. There's more for us to do to push this forward, but there's also more collaboration that's needed for creating the curriculum, for creating the lab modules, the equipment lists, to integrate all of that equipment into a package that can be delivered effectively and surmounting those sales, marketing, distribution challenges that are going to come up. But ultimately, I see this like my dream here is an easy button for quantum. And there's a couple pieces there, right? There's it needs to be easy for people to get it in their hands. So like a one-stop shop for a new to quantum educator and students to collect everything that they need that shows up in one shipment or one purchase and allows them to be successful on their first try. And I think that first try is also an important piece. We may only get one shot at kind of getting this into their hands, into their classrooms. And the other piece here is, we want this to have a wide reach. We want to reach as many people as we can. Obviously, there's going to be some funding challenges for smaller institutions, even four-year colleges, two-year colleges, community tribal colleges, even down to the high school level. And sort of the vision that I have here is imagine if characterizing superconducting materials is as ubiquitous in a high school science lab as a frog dissection. Like, we made it. So in closing, the workforce education is a pillar of the Monarch Quantum Foundry. Montana Instruments is in Bozeman, Montana. So, Montana State University is right in our backyard. We are actively working with them to try to define our path forward in this and figure out how to make a hands-on quantum teaching lab a reality. And like I said, there's a lot of collaboration that's still needed. So if anybody has curriculum or would like to be involved, please contact us, contact Monarch. We'd love to have your help. So thank you very much for your time and brain space today.